or recording. And then saw that few difference between the density, okay, the volume of water displayed by the crown and the density of water displayed by the gold. And so he drew his conclusion. Then the guy was invited, and in fact, he conferred. And so Archimedes was hailed as the best scientist of all. Okay, so that's the history behind Archimedes' principle. Okay, he just used the volume of water displaced by the crown, volume of water displaced by the gold, and then compared to draw his conclusion. All right. Then he um, put together a principle or law, what we can also say as law, based on his observation, and stated that when a body, if you have a body and the body is fully, okay, or partially immersed in, I'll write it for you, okay, if the body is fully or partially immersed in anything fluid, either gaseous or liquid, the body experiences an upward force, upthrust, okay? And this upward force is equal to the weight of the fluid displaced by the body. So all that Archimedes is saying is that the upthrust or the upward force is equal to the weight of fluid displaced. That is Archimedes' principle. When a body is fully or partially immersed in fluid, there is an upthrust which is equal to the weight of fluid displaced by the body. That is Archimedes' principle. Things you have to note. You see, you have to note that when a body is immersed in fluid, the weight of fluid displaced, okay, weight of the fluid displaced is equal to the weight of the object or part, okay? So weight, let me recraft it. When the object is fully, when object is fully or partially immersed, volume of fluid displaced is equal to the volume of the object. Yes, but this is not Archimedes' principle. Archimedes' principle. When the body is fully or partially immersed, the volume of fluid displaced is equal to the volume of the object. But this is not Archimedes' principle. Archimedes' principle refers to the upthrust being equal to the weight of the fluid displaced. Take note. Even though this is a fact, but this is not Archimedes' principle. Please, are you okay? Are you okay?
Yes, please. Yes.
All right. So let's look at a simple experiment, okay, to describe Archimedes' principle or confirm an experiment. I think I have to adjust. An experiment to prove Archimedes' principle. An experiment to prove Archimedes' principle. The principle simply says that upthrust is equal to weight. Hello.
I don't know what you're writing. It's very good.
It's not clear.
Yes, please.
Oh. Is it better?
Yes, please. Thank you.
So upthrust is equal to weight of fluid displaced. Upthrust is equal to weight of fluid displaced. Let's look at materials needed for the experiment. Every experiment will require some materials. So one will need an irregular object, an object or objects. It can be a stone. We'll need Eureka can. We'll need an electronic balance. We'll also need a spring balance. Then water. So a stone, Eureka can, electronic balance, spring balance, and water. In the lab, one of the quickest way of determining upthrust is this. You use a spring balance to weigh an object to get its weight in air. So this is the spring balance. You suspend the body or the stone around to get the weight in air. So by doing so, all that we want is to determine the weight of the stone in air. So record the weight of the stone in air. W subscript A. W subscript A is the weight of the stone in air. After recording the weight of the stone in air, you also weigh the stone when immersed in fluid. And here we use water. Okay, so we weigh the same stone suspended on the spring balance, we weigh it in air when it is totally immersed in water. Okay, so the same stone is also weighed in water. So we record the weight of the stone in fluid or water. Record the weight of the stone in water.
Mr. Edia, please, can you adjust the screen?
I'm coming in. Is it better?
Yes, please.
Okay, so we weigh this and to determine the weight of the stone in water. Now the observation is that, you see, when you weigh an object in air, okay, what you have will be the real weight. So W A, weight in air, is equal to the real weight. I earlier told you that when you weigh an object, when you try to even carry a friend on your laps when you are swimming in water, it feels easier, meaning that within the water medium, something as some force within the water helps you out. That is why you feel your friend feels lighter when you carry him in water. Okay, so it implies that weighing the object in water will be supported by the upthrust U. So the weight of the object recorded in water becomes the apparent weight or false weight. So W in water or fluid becomes the apparent weight, sometimes also called as the false weight. It is apparent or false because that's not the real situation. Please, are we okay? Class, are we okay?
Yes, please.
Good. Finding or determining the difference between the real weight and then the apparent weight would give you the upthrust or the lost weight. So the lost weight, which is the upthrust, equal to the upthrust or buoyant force or upthrust or upward force or buoyant force is equal to the real weight minus the apparent weight. So in the laboratory, one of the quickest way of determining upthrust is that weigh an object in air, weigh the same object in fluid or water, and the difference between the real weight and the apparent weight will be equal to the upthrust. And so this is equal to WA, W subscript A minus W subscript F. And we are using F for fluid, A for air, F for fluid. Don't forget, it can be any other fluid, okay? Or it can be any other liquid. So I don't want to use water, but F for fluid. That is one way of determining upthrust. Any question? Agosia?
If you use WF for meaning fluid, but you said fluid can be air or
Yes. That is even why I'm using, you see, over here in this particular experiment, Akosia, we can use air. We can use any other liquid, but not air. Okay. So, or the best way out is instead of including air, let's bring air, liquid. Are you okay?
yes, please.
Liquid will do it best. Zuvier, are you there? Are you there?
Yes, Mr. Adria.
These days you don't ask questions. Can I refocus the camera to a different position if you are done writing here?
Yes, please.
Okay. So that is one way of calculating for upthrust. Weigh an object in air, get the real weight. Weigh it in fluid, get the apparent weight. When you subtract the apparent weight from the real weight, you get the upthrust. Another way out, you see, Archimedes' principle is saying that upthrust is equal to the weight of fluid displaced. So another possible way out is that, okay, when the object is immersed in a fluid, let's find a way to get the weight of the fluid displaced. Okay, or let's find a way to get the water or the liquid displaced, and when we determine its weight, it will be equal to the upthrust, because Archimedes is saying upthrust is equal to weight of fluid displaced by the body immersed within the fluid. Please, are we fine? So we modify this by immersing the whole thing, the stone, okay, in a Eureka can. And Eureka can has this feature. It has a spout. It has a spout. Let me bring the spout here. It is similar to this cap with a long, okay. I think it's similar to Buddha without outlets. So we have the spout here. Now, what do? You initially fill the water level to the spout. You fill the water level to the spout because we are interested in determining the weight, the volume of the liquid displayed, or the volume of this object. When the object is immersed totally, the overflown water would equal to its volume. So we are interested in determining the volume of the object. And so we have a spout filled, we have a eureka can filled to the spout. Okay, this long outlet is what you are calling as a spout. Now you weigh a beaker when empty. So we have to have a beaker here. I have to determine the weight of this beaker when empty. Weight of empty beaker. And the reason is that if it is filled with water, you reweigh, okay, to determine the weight of the water collected. That is why you have to first and foremost know the weight of it when it's empty. Please, are we fine? Are we okay?
Yes, please.
Okay. So you gently lower this, okay, the stone tied to the thread into the eureka can. Okay. And the moment you lower it in, there will be overflow of water. The overflow water will certainly be equal to the volume of the object. Okay. So after collecting the displaced water, you reweigh this. Okay, let's assume the mass of the empty can. So assuming mass of empty can is equal to m naught, and I'm talking about it in terms of mass because we are using the electronic balance to determine this. So mass of empty can, then mass of displaced water or liquid plus can is equal to m1. Therefore, the mass of water displaced which will be equal to m1 minus m naught. So m1 minus m naught gives us the mass of the displaced water. Archimedes is saying that the upthrust equals weight of fluid displaced. So what we have is the mass of water displaced. We express it or we convert the mass, okay, as weight. And how do we do that? How do we do that conversion? How do we convert the mass of what fluid displaced or liquid displaced to weight so as to satisfy Archimedes' principle? Yes, how do we do that? Hello? Hello? Yaba? How do we do that?
We multiply by gravity.
Okay, so Yaba is saying that we multiply by gravity. Do we all agree? All right,
Yes.
so if the mass is in gram, Yaba, if the mass, okay, after the deduction, whatever you got is in gram, then you convert the mass in gram to kilogram. Okay, then you multiply by 10 meters per second squared to get the weight. Or because 1 kilogram weight is equal to 10 Newton, it implies that if you have 1 gram 1 gram mass, this will be equal to 0.01 Newton. Okay, maybe I have to take you through gradually. Weight is equal to mass times acceleration due to gravity. So if I have a mass of 1 kilogram, its weight will be 1 kilogram times 10 meter per second squared. So 1 kilogram would give you a weight of 10 Newton. If I have 1 gram mass, what will be its equivalent weight? Okay, 1 gram is equal to, let's express 1 gram in kilogram. 1 gram expressed in kilogram. Yes. Quick one.
0.001.
So 0.001 gold kilogram. Meaning if I have 1 gram and I'm expressing it in weight, it is equal to its mass in kilogram 0.001 times 10, which will be 0.01 Newton. Okay, so with this, I'm always saying that if you have 1 gram, it is equivalent to a weight of 0.01 Newton. Okay, so when I have masses in gram and I have to convert, I don't need to go back to convert to kilogram. All that I do is that multiply the mass of 1 gram by the weight, which is 0.01. So 10 gram mass converted to weight will be 10 times 0.01, and I'm good to go, which is 0.1 Newton. Is that okay? So if the mass is in kilogram, then times gravity. If it's not in kilogram and it's in gram, all I do is that multiply that by 0.01 and you have the weight in Newton. Please, are we okay? Are we okay?
No, please, I can't go back.
All right. This is, we calculated for the mass of the water display and then got M1 minus M0 is equal to the mass of water display. Archimedes' law is saying that F is equal to weight of fluid display. So it means I can't just have this in mass and then I'm done. I have to convert it to weight, okay, to satisfy Archimedes' principle. What I'm saying is that if the mass is in kilogram and you want it, you want the equivalent weight, all that you do is that straight away the mass in kilogram times acceleration due to gravity, which is 10 meter per second squared. Then you have it. Are you okay? If the mass is not in kilogram and it's in gram, if mass is in gram, all that you do is that ideally you have to convert it from gram to kilogram and multiply by 10 meter per second squared. Okay, but you can also multiply straight away. I know 1 kilogram would give me a weight of 10 Newton. So if I have 1 gram, 1 gram is equivalent to a weight of 0.01 Newton. So there is no need of me converting the mass in gram to kilogram before multiplying by gravity. All that I do is that the mass as I had in gram multiplied by 0.01 Newton, and I have the weight of that. Are you okay? Are you
Yes.
okay? Example, let's assume that the mass of the empty can is equal to 15 grams. Okay. Then after collecting the displaced water, the mass of the displaced water plus can is 32 grams. It means that the mass of the water displaced will be 32 minus 15. Okay, and this is equal to 17. All right. Now, to satisfy Archimedes' principle that Acras is equal to weight of the fluid displaced, I have to express this 17 gram in weight. So weight, so Acras, which is equal to the weight of fluid displaced, weight of water displaced, is actually mass of water and gravity. Okay. Now, the mass of water, I'll be tempted to, let me express the 17 grams in kilograms. So 17 divided by 1,000 times 10. Okay, which is 0.17 Newton. It means that is the Acras. Okay. The alternate way out is that instead of converting the mass in gram to kilogram, okay, all that I do is that Acras is equal to 17 times 0.01. Please multiply 17 by 0.01.
Mr. Dia is the same.
It's the same. So there is no, if you have the mass in gram, there is no need of you going back, converting it to kilogram before you multiply by gravity. 1 gram is equal to a weight of 0.01 Newton. Are we fine? And you get whatever you are looking for. Any question? Akosia, Epia, Kelly, Zuvier, Yaba, Asante, Otua, Bushra, and all the names. Any question? Akosia, go ahead.
You said that please, the 0.01, is it from 1 divided by 1,000?
Akosia, you were not paying attention.
Oh, I was paying attention.
I said 1 gram, 1 kilogram, okay, has a weight of 10 Newton. Okay, so 1 gram mass has a weight of 0.0. So if I have mass in gram, okay, I don't need to convert it to kilogram before. All that I do is 17 times 0.01. And I'll have the same thing as when I've converted it into kilogram and it's multiplying by 10. Abuja, are you okay?
Yes, please. Thank you.
All right. Because, are we done writing? Can I clean it? Hello, can I clean it?
Yes, please.
Let me pick this call and then get back to you. Okay, I'm coming. Hello. Okay. Okay, so because Acras in the first experiment conducted, Acras is weight in air minus weight in liquid. And in the second experiment where the object was immersed in an aerator can, we got the same atlas to be equal to weight of liquid display. Weight of an object, okay, is the product of the mass of the object and then gravity. So we can say that this weight of liquid display is equal to mass of liquid display times gravity. We are breaking down weight into mass and gravity. Class, are we fine? Are we fine? Give me feedback. Okay. What is mass in terms of density? Density and let me break it down further. So this is equal to mass of fluid or liquid displaced times gravity. What is mass in terms of density and volume? What is mass in terms of density and
mass is density times volume.
Okay, so it means that this mass of liquid displaced can also be density of the liquid displaced times volume of liquid displaced times gravity. Okay, so the same atlas can be expressed in terms of these three: weight of liquid displaced. Atlas is also equal to mass of liquid displaced and gravity. Atlas is equal to density of liquid displaced times volume of liquid displaced times gravity. Class, are we okay? Are we okay? Good. Because of that, since this is atlas and this is also atlas, we can say that WA minus WL is equal to density of the liquid displaced times volume of the liquid displaced times gravity. And this is a very important formula in solving Archimedes principle problems. That atlas is equal to this. The left-hand side is equal to atlas. The right-hand side is equal to atlas. And so we can equate the two of them. Are we fine?